Hey, I'm Aaron Thorough, and this is my Galaxy Assessment for AST 322 Fall 2025 semester. For my assessment, I chose the Giant Galaxy Seen in 3D by NASA's Hubble Space Telescope and Keck Observatory article. There's a link to it at the bottom there. For the agenda, I'm going to introduce Messier 87, the elliptical galaxy, why it's unique, where it falls on the Hubble tuning fork, a little bit about its active galactic nuclei. We're going to discuss the research from the article. We'll discuss the results, and if it challenges any of our current understanding of past research and what this means for the future of scientific research. So a little bit about M87. It does have an AGN, was active galactic nuclei. This photo here was taken several years ago. It was the first ever released photograph of a accretion disk around a black hole. It was taken with the Event Horizons Telescope, which is a multi-telescope array. And it was released April 10th, 2019. This made a lot of us space nerds happy when we saw this. Now, in the photo, you can't actually see the black hole. It's that dark part there in the center. And that little ring donut looking thing is superheated gas that's swirling around the central region there, which is the black hole, which you can't actually see the black hole. But that's called the accretion disk. Now, even though that previous picture was the first image released, this photograph here shows the first time data was being observed during that campaign, which was 2 years prior, April 11th, 2017. And a year later, the Event Horizons Telescope followed up that data of the accretion disk, and you can see some subtle changes there, especially where the bright parts are traveling around that black hole. I just want to throw in a quick slide here of the Event Horizon Telescope. This shows all the locations of the radio telescopes and radio arrays that were used to image the or not the event horizon, the accretion disk around the black hole. And the reason we could do that with such good angular resolution is because the sheer size of this telescope, it's basically the size of the whole Earth. So this is our Hubble Space Telescope photo of M87. It's our elliptical galaxy. This galaxy lacks dust and gas. It has a lot of older stars, a lot of yellow stars and red stars and globular clusters. Because it has a lack of gas and dust, it's not actually producing a lot of newer stars. As we've discussed before, it has an AGN, which is the supermassive black hole in the center with the accretion disk. And that accretion disk is producing this galactic jet here that's coming from the center of that galaxy. So this is our Hubble tuning fork. It's our current classification scale of the galaxies we see in the sky. On the right are the spirals. Bottom part of the fork is the barred spirals. Top part of the fork is our regular spirals. Where the fork meets the handle there at S0, that is our lenticular galaxies. We think those are mergers of spiral galaxies, kind of causing the spiral galaxies to lose their shape in their arms. And on the left, we have our elliptical galaxies. There are these ellipsoid shapes, or 2D ellipsoid shapes. And right there on the left, E0, that's where M87 falls. It's almost has no elliptical shape to it. It's almost a perfect circle. But with our study, we're going to find that we think it moves down the line. And we'll see that later. So if you remember in class, we had a way to classify the AGNs, and we start there right at the top. We know that M87 is a radio loud AGN because we see radio radio waves coming from it. So we go off to the right there. We ask ourselves, is this a radio galaxy or is it a blazar? If we remember from the modules, blazars have the AGN jets that are pointed directly at us, so they look really bright. And as you remember in the photos, we could actually see the jet coming off to the side. So we're going to just label that as a radio galaxy. Now for the next part, it's the Fanaroff-Riley classification of AGN, which is the FR1 and FR2. M87 is specifically an FR1 because it has low radioluminosity. The jets are brightest near the core, and they decelerate rather quickly and become diffuse the further out they go. And the lobes from that jet are edge-on darkened. So this photo depicts how the jets come about. You can see that red color there in the center. That's the accretion disk spinning around the supermassive black hole. And you can imagine these supermassive things have these really strong magnetic fields. And so what happens is some of the material from the accretion disk gets sucked up into these magnetic fields that are pointing away from the north and south pole of the black hole. And as they speed up, they release photons, and we call that synchrotron radiation. So here is an animation of M87 and sort of a 3D model of what it looks like according to the researchers from UC Berkeley. It's kind of hard to classify elliptical galaxies because we see this like 2D shape in space, right? We see a 2D galaxy on our 2D celestial sphere. So we don't really know just by looking at it the shape of the galaxy. Spiral galaxies are a little bit easier to classify because they're these kind of flat disks with spiral arms. And if we see a face-on spiral galaxy, we can determine whether it's a barred spiral or what type of spiral arm structure it has. So the team at UC Berkeley, using the Hubble Space Telescope and the Keck telescope in, I do believe, Mauna Kea, they measured the 3D shape of M87. And the way they did this is that they measured groups of stars and the motions of those stars that are spinning around the black hole in the center. And they couldn't actually resolve individual stars in this galaxy. It's super far away. But what they did was they compared this to kind of like measuring bees swarming around a hive. They would find these groups and clumps of stars and measure the relative velocities of those. So with the new observations that they made, the scientists at UC Berkeley, they were able to accurately determine the mass of the supermassive black hole at the center of M87. Previously, with the Hubble Space Telescope, using the hot accretion disk at the center and the rotation of it, they came up with the estimate of 2.4 billion solar masses of that black hole. The Event Horizons Telescope, using general relativity of that hot accretion gas, they came up with 6.5 billion years. Now, our UC scientists, measuring the masses and velocities of the stars around the center there, they came up with 5.4 billion solar masses, which they do believe is a more accurate measurement of the supermassive black hole. Here's a little quote from some of the scientists and researchers that were doing this study. says, now that we know the direction of the next rotation of stars in I apologize. Now that we know the direction of the net rotation of the stars in M87 and have an updated mass of the black hole, we can combine this information with the data from the Event Horizon Telescope to constrain the spin. So basically what they're going to do is they're going to combine their data with the Event Horizon data to get a better idea of the spin of the black hole and the accretion disk at the center there. And what what they did, this is kind of funny, was they compared the shape of M87 to a triaxial potato. So that's a picture of a triaxial potato, and we'll go into that in the next slide. So previous studies, when measuring these elliptical galaxies, scientists were using axisymmetrical assumptions to measure the shapes and masses of the supermassive black holes in the center of these galaxies. And you're probably wondering, well, what's axisymmetrical? And the photo on the left there of that football, I put that there to help illustrate. And I put a red line down the center. And so if you imagine that red line in the center of the football and not actually on top of the football, you can kind of imagine that everything is kind of symmetrical around the center axis of this. So it's kind of very nice, neat, uniform, and kind of perfect. And that was an assumption we were making to measure the center of these black holes, or the center of these galaxies where the black holes were. So when we're talking about triaxial, what it means is there's not really any true uniformity. Like the potato on the left, to bring up potatoes again. You can see, and if you imagine that line going straight through the potato, not actually on the surface of the potato, you can see that it's actually lumpier in certain areas. It's got a weird twisted distribution of mass around that axis, and it's not perfect. I almost said it's not beautiful, but I actually think that's more beautiful. That it's not perfect. I think giving it its own unique characteristic is a little bit more beautiful. And I think it gives a lot more information and data on the galaxy than just having it this assumed perfect football shape. So with one of the assumptions or one of the conclusions that they came up with is that it shows the massive elliptical galaxies are actually truly triaxial and not axisymmetrical. And that's very important for understanding the structure and evolution of these galaxies. The assumptions of the axisymmetrical can make incorrect estimates on the mass of the supermassive black holes at the center of these galaxies, just as the Hubble Space Telescope did in 1995. So the article that I read was referenced from a research paper that was peer reviewed, and this graphic comes from that. These are kinematic maps that show the general rotations of areas of stars in the galaxy. As you see on the left there, the red and blue represent blue and red shifts of spectral lines associated with the velocities of the star regions that I was talking about that they were measuring. They then use that information to determine the three axes by using three different components. The central or the supermassive black hole at the center, stars, and also the dark matter halo around the galaxy. The central image shows these axes of M87. And for the stellar masses, they use the stellar mass to light ratio, which I thought we looked at or used in some of our modules, but I could not find it anywhere. But that equation there at the bottom left looks really familiar. So this here is taken directly from the paper itself too. On the left, you get the sigma, which is the kilometers per second. And on the x-axis, you get the radius in arc seconds. The work from this study is the blue lines there with the error bars, as you can see. And then some of the other studies were also plotted along it as well. Are these results expected, or do they challenge our current paradigm? Well, these results actually do challenge the current paradigm because we were making assumptions. That was our current way of thinking. Our best current way of thinking was actually just assume, kind of like we did in class, that everything was this nice, neat, orderly way, when in fact the universe is very unique and galaxies are very unique and they have their own shapes. So we can actually get more accurate measurements of the supermassive black holes at the center of these. Um, you know, if we take the assumptions out of the data and add more empirical data, we get better information and better calculations. The significance of this work is that it challenges the common assumption that the massive galaxies like M87 are axis symmetrical. And it shows that M87 is truly triaxial, and that our black hole estimates depend strongly on the galaxy shape. The study pushes the field forward, I think, in providing more accurate models, and I think we should be revising our earlier uh, expectations of what these galaxies were. I also think, in the future, once we um, measure a lot more of these galaxies, we may need to update the Hubble tuning fork for elliptical galaxies. If we look towards the future, I think we should apply this method to a wider sample size of elliptical galaxies and to see if it actually applies to more or all of them. That way we can get more accurate measurements of the supermassive black holes and AGNs in the center of these galaxies. And I think that'll provide more, better, accurate data for understanding of galaxy formation, evolution, and the future of cosmology. So I'm going to propose this to future cosmologists and astronomers. I propose that we make a potato handle to the tuning fork, P0, P2, and P4. And it can be determined by the size of the elliptical galaxy. We won't call it elliptical anymore. We'll call it potato galaxy. And the lumpiness of the triaxial shape. I think that's in tune for what we're doing. And with that, I just wanted to thank you very much for watching my video. And this is the JWST near cam, which is near infrared cam of the M87 jet hanging out there. You can actually see a little bit more detail in it. Thank you and have a great day.